field theories, then you ask the question of what is, how can I understand what the world is made of? And for that, you need to, in some sense, you're interested about the ontology of the theory, for instance. And similarly, you can ask the question about theories of space and time. For GR, you can ask the question, what is space and time according to GR? So these are slightly different questions than you usually ask within physics, but they're the kind of more of ontological kind. They go beyond what is beyond the empirical questions of the theory. In philosophy of science, you kind of take a step back. The content of the theories become less important. You look more interested about the kind of methods used and the development of science at large. And this talk, although it's related, the topic matter is particle physics, it is more of a kind of general philosophy of science talk, namely about the topic of scientific problems, now applied to the context of particle physics. And I came to start to work on this as Megan was mentioning. I'm part of a kind of big research unit. It's called the Epistemology of the LHC, which aims to, so it's a kind of interdisciplinary research unit that tries to address questions about the LHC from a kind of humanities point of view. So we have sociologists, we have historians and philosophers of science and philosophers of physics, who together with the physicists, both experimental as well as theoretical physicists, try to address certain kind of foundational questions. And in that context, so my work on scientific problems grew, and I will tell you a little bit about that, but also more generally something about how scientific problems shape theory development. Now, if I'm not mistaken, I saw a hand go up. So I think it's best if it's like a clarificatory question. Feel free to raise your hand. Otherwise, maybe for larger questions, we can just postpone it to the end, if that's okay. Actually can't see the hands now, but okay. So I'll just continue until I'm interrupted, which is fine. Feel free to do so if something is unclear. Okay, now I can see. Okay. Okay. So, so since we're talking about scientific problems, let me just give you a list of some of those so you know what I'm talking about. These are a list of unsolved problems in particle physics and fundamental physics more generally, which probably most of you have heard of already. So for instance, questions like what is dark matter, what is dark energy, the baryon asymmetry problem, which you probably have heard this week as well, about the asymmetry between matter and antimatter. Why is there more matter than antimatter? Then the hierarchy problem, why is gravity so weak compared to the electroweak scale? Small neutrino mass problem, why is the neutrino mass so tiny? Similarly, the small Higgs mass problem, the strong CP problem, gauge coupling unification, or the scientific problem of finding a consistent theory of quantum gravity. All of those are kind of problems in current fundamental physics, which are being addressed in everyday scientific practice. So what is, why look at it from a philosophical perspective? Well, it kind of started with a paper that Thomas Nichols, philosophers of science have been talking about scientific problems before, but it's mainly started with Thomas Nichols in 1981 when he wrote this paper called What is a Problem That We May Solve It? So he went a step back and asked the question, what is the problem in the first place that and why should we solve it? He didn't actually address the second part, but it's really about the kind of what is it question, what is a problem? So from a philosophical perspective, you might be interested in asking the question, so what is a scientific problem that we may solve? And which corresponds to the question of what it actually constitutes, what it is constituted of, right? So what is it made of? What is a scientific problem? How can I kind of phrase it in more abstract terms? Then once you have defined that in some sense, there might be many things that satisfy which of these actually need to be solved, right? So once I have a kind of abstract definition of that, many things may satisfy that definition, but it still doesn't tell you which of these actually need to be solved. So are there more and less urgent problems? Purely from intuition, this is the case. Do we have a way to understand why this is the case? Are there more and less justified problems, or even unjustified problems? What does it mean for a problem to be unjustified? And even if you have the problem, then the question comes up, how should I go about solving those, right? What kind of methods am I allowed to employ to solve the problem? So if you pose these questions to physicists, I mean, not all, but kind of attitude as well, scientific problems are those that we consider to be scientific problems, right? It's just a list that you saw we work on, and that's it. And we consider some more urgent, then those are the more urgent ones, and the other ones are less urgent, right? They actually usually don't address this second kind of question. And then they go ahead and solve it the way they are used to, right? You learn all the methods in university. If you learn quantum field theory, you learn certain methods to solve, to calculate cross sections, etc. You learn these in textbooks, etc. How to solve those, and these are the methods by which we can solve the problem. So why kind of look at it more abstractly? Why this kind of more general philosophical question of identifying what a problem is? This seems rather abstract and philosophical and rather irrelevant for scientific practice. And this might very well be, there is a kind of reason to do that, even independent from the fact that it can be of use for the practicing scientist. But the current situation is that simply that these answers are not uniformly answered within the scientific community. And in those circumstances, it might be helpful to kind of reflect more abstractly about these issues. And this is something I want to kind of introduce you to today. And let me illustrate the current situation a little bit with an example from, well, current fundamental physics. So we have many, so fundamental physics is in a kind of precarious situation currently. And you have, on the one hand, if you look at particle physics, you have strong disconfirmation of most of the theory landscape, right? So at the LHC, you made the experiments ruled out much of the theories which have been proposed beyond the standard model. And on the other front, you have theories like theories of quantum gravity, grand unified theories. You have hypotheses within astrophysics and cosmology, where you don't expect in the foreseeable future any experiments that are able to confirm or disconfirm these hypotheses. Theories of quantum gravity are usually at the Planck scale, and it's just very difficult to, well, no collider can get those energies up to the Planck scale. Similarly, the gut scale, you can test indirectly by, for instance, proton decay. But again, it's several orders of magnitude beyond what colliders can reach. But also in astrophysical and cosmological context, if you think about inflation, or if you think about Hawking's analysis of black hole radiation, that black holes radiate thermally, it's a hypothesis about black holes, which is incredibly difficult to test. So this leads to kind of difficult situation. On the first front here, in current particle physics, once you don't have much guidance for further theory development, right? You develop a theory based on certain principles, and all of those, most of them at least, were ruled out at the LHC. So you could ask the question, so what now? The kind of methods that I used to develop theories turned out to be not very helpful. So what kind of theoretical guidance, the principles that I can rely on, do I still have? And there doesn't seem to be much of the guidance left in the current LHC physics, high energy physics more generally. And on the second front, with theories of quantum gravity and so on, you cannot expect any guidance from experiments, right? So you are developing theories, and you don't have any way to kind of assess those theories in the absence of, so, well, you don't have any experiments to test those theories. So the straightforward point is that, like, well, this has an impact on scientific practice. The way people are working, the methods they use are changing. So it has an impact. It has had an impact already. And the question that comes up is, of course, how should scientific practice change? It changes but how should it change? And there are changes, of course, in two different contexts. One, in the context of discovery, the way I aim to develop new theories. And the second one changes with the context of justification, in the sense of how can I assess my theories when I don't have experiments to test them with? So with the first, so you see alternative kind of ways to develop theories, which were at some point maybe less acceptable, are now being pursued. Think about multiverse theories, etc. And you have methods of within the context of justification, so within the context within which you try to test your theory, which are now not experimental, but maybe what is sometimes called meta-empirical. One proponent of that is Richard David in Stockholm, who has introduced a kind of method of theory assessment, which goes beyond the experimental. And it's something which is quite liked by, for instance, string theorists, who rely on these kind of meta-empirical reasoning to confirm their theories. Now, I've told you some of the kind of issues involved in this kind of precarious situation, but what does that have to do with scientific problems? I didn't have to tell you about anything about scientific problems here. Well, let me go to an example. Here you have two prominent physicists. You have the experimental physicist, Maria Spiropoulou, and the theoretical physicist, Joe Lipton, who in 2014 wrote a Scientific American article in which they said the following: "It is not an exaggeration to say that most of the world's particle physicists believe that supersymmetry must be true." This is my emphasis here. That must be true. So this is a kind of very strong claim. This is a strong claim because supersymmetry is a proposed extension, the kind of proposed extension of the Poincaré symmetry, extension of the space-time symmetry, based on which you can develop models beyond the standard model, which have been developed for now almost 4 decades. And none of those has been experimentally confirmed. So to say something like this seems to be very strong. And you could ask the question, so on what basis do they assess that theory to that strong extent? And this is not something just in the context of supersymmetry. You can see similar kind of assessments also with respect to neutrino physics. If you look at here, you have Ravindra Mohapatra, who in an article in 2004 said the following about the Seesaw mechanism, to a much lesser strength in sense compared to Lipton and Spiropoulou, but still, it's a kind of assessment already of the mechanism. That's what he says about the Seesaw mechanism. The Seesaw mechanism is by far the simplest and most appealing way to understand neutrino masses. It not only improves the aesthetic appeal of the standard model by restoring quark-lepton symmetry, but it also makes weak interactions asymptotically parity conserving. Furthermore, it connects neutrino masses with the hypothesis of grand unification. So there are several things which speak in favor of the Seesaw mechanism, so in some sense speak in favor of it, independent from it being experimentally tested. And these are sometimes aesthetic aspects, but also kind of more, it solves certain problems. It relates, you remember, grand unification is one of the problems I mentioned before. It relates to that. And there is much more to be said about this as well, but I will focus more on supersymmetry because that has kind of driven the experimental search beyond the standard model in the last couple of decades. So let me go back to the supersymmetry case from Spiropoulou and Lipton and ask the question, so what are the arguments you can find for supersymmetry? Well, if you look at if you kind of look at textbooks, Zuzi is short for supersymmetry, textbook introductions to supersymmetry, you usually find the following kind of reasons which speak in favor of supersymmetry. First of all, it solves the naturalness problem of the Higgs mass. I will tell you more about what that is later. So it provides a candidate for dark matter, one of the big problems, open unsolved questions, right? It can solve the baryon asymmetry problem. It can solve the problem of gauge coupling unification. You can show that without supersymmetry, the different couplings do not come together. And when you extend it, there are models beyond the standard model which allow you for a kind of better gauge coupling unification. So in short, what speaks in favor of supersymmetry is it solves a lot of problems. It solves a lot of scientific problems. Well, so it is there is no doubt that scientific problems are one of the main driving forces behind scientific practice, both in developing and assessing scientific theories. Now, so far, all could be good. Now, the problem is, as I said, most of the theories beyond the standard model have been disconfirmed. So the current non-observation of supersymmetry at the LHC has led to the attitude that people say, maybe the problems were never justified in the first place. This is an attitude you can find, for instance, with Sabine Hossenfeller and also many others. It's actually wide shared opinion that maybe we should never have considered, for instance, the naturalness problem of the Higgs as the genuine problem. But once you kind of see that shift, so you propose a problem, you find solutions to that problem, the solutions, which are the theories, turn out to be kind of disconfirmed, then you kind of go back and say, well, the problems are maybe not justified. But the problem kind of appeared independent from the solutions to some extent at least. And so the question comes up, maybe we should kind of assess problems before we start, right? In some sense, what are these problems? What makes them problems? And what does it even mean to say they were never justified? Does it make sense to talk about problems in this way? So this brings us back to the kind of more philosophical questions I posed at the beginning. So what is a scientific problem? And I will focus more on this first one. I will say, if time allows, I will say something about the second one and probably less so about the third one here. Okay, so this is, yeah, I know this was the introduction. So now I will get to the outlines of the talk, which is what is a scientific problem, which is kind of general question I want to address. Then how do problems relate to their solutions? And when I was thinking about kind of developing this, I was also thinking about what could be useful for you. So once you have that, once you have a kind of more formal account, you could also, from this formal perspective, ask the question, what are strategies to solve problems? And I will kind of mention several and also link them to how they were applied in the context of particle physics. And if time allows, I will get at the end to talk about the which problems are worthy of pursuit. Just kind of spoiler, I will not give you a satisfactory answer to that because this is a difficult question. But realizing that it's difficult is already something which I hope is useful. Okay, so let me start. So what is a scientific problem? Well, there is philosophical literature. There's actually not that much philosophical literature about that, but there is some philosophical literature. And here you have a slide with kind of a list of the literature on this, and I'm not going through them. Mainly because, I mean, this is just to give you the way how the ideas about scientific problems develop. But I will kind of more focus on this very first point, because usually when you talk to scientists and physicists more specifically, this is the kind of attitude one usually has, right? So the positivist model of problems is that, well, what are scientific problems? It's just empirical facts which are in search of an explanation or prediction. Imagine going out, looking at the road, saying, oh, I would like to understand how that comes about, right? I want to have an explanation for that. So it's nothing, just this kind of empirical fact you have, and then you need some explanation or prediction of that fact, and that is provided by the theory, right? So you have this kind of independent empirical fact on the one hand, and you have the theory, which then is the solution to that to that scientific problem. Now, there is this simple picture is insufficient. That's why there is a huge amount of literature after that, and most of that didn't recognize it till Nichols came about, but also maybe probably Radin. But the first problem is that it's not straightforward to understand what kind of empirical fact needs to be explained or predicted in the first place. So consider a falling object. This is my ball. I play with it when I'm bored. So this is a ball, and I could consider this object, and I just drop it, right? I let it fall, right? I could, then there are several questions. So this is something I'm observing. And so I could ask the question, so what the first question we need to kind of address is, when I observe that, what do we want to explain? What do I want to predict with respect to that falling ball here? So I could ask, for instance, why fall, right? Or I could ask, how fast does it fall? And all of these are kind of legitimate questions to ask. You think, and you're right by thinking that, but well, let me get to that later. But so these are different questions you might want to pose, which then need to be explained or predicted. So you could also ask the question, what kind of data should I collect to kind of also test that more clearly? This kind of what elements of this empirical fact are relevant for explanation, right? So is the mass of that object, so if I drop that, is the mass relevant or not? Should I measure the mass? Is the composition important? Is the size of that object important? Is the color of it important? Is the position of that important? And while I'm mentioning those, several of you who are studying physics, you're going to say, of course, the composition is irrelevant. The size is irrelevant, right? You know that the color, of course, is irrelevant, right? But now think pre-theoretically, pre-Newtonian, right? The very questions you ask about that are not determined by that observation of that falling object by itself, right? It is with a certain background knowledge that you kind of address that question. And within that, the very questions that are that need to be addressed are posed, right? So it is within this kind of theoretical framework, or as Kuhn would say, in your paradigm. So when I think of kind of Aristotelian, I'm now going 2,000 years back, and I look at this thing falling, and I ask, so why does it fall? And then Aristotle says, well, there are several elements. We have earth, then we have water, then we have air, then we have fire. And all of these objects actually have a natural place, right? So this is made up of earth, and it wants to go back to the earth, right? So if I drop it, it just wants to go to its natural place, right? So here I have an explanation. It actually tells me if I drop it, it's going to go down, right? Similarly, if I go underwater and swim and I breathe out, according to Aristotle, I would expect that when I breathe out, the air in my lungs actually goes up, which it will, right? This is what Aristotle predicts, and that's what happens, right? So I have kind of a question. I have given you an explanation within that context, within that Aristotelian picture. Now, within the Aristotelian picture, the question is how fast it falls. It doesn't come up. It's not a quantitative theory. There are approaches now, modern ways of kind of giving a quantitative analysis of Aristotle, but you don't have to, right? And especially Aristotle didn't do that. So the question of how fast it falls, these concepts were not there yet. So this is not a question that comes up, which needs to be explained or predicted. Similarly, the mass is important according to Aristotle, right? So if it's heavier, then it falls quicker. If it's lighter, then it falls slower. Well, if you go to Newtonian gravity, you know the M cancels, right? So it doesn't matter how heavy that is. And the only reason why we observe something different is because of air resistance, right? But even within the Newtonian picture, everything, now the second question, how fast it falls, makes sense. Why it falls due to gravity. But you know that, for instance, the color doesn't matter. It's not part of the equations. They don't play a role there. So you see that the very kind of the empirical fact and what features of that are important is not determined independent of the theoretical framework you're in. This is nicely put here by Thomas Kuhn, a historian and philosopher of science, who in his famous work, The Structure of Scientific Revolution, said the following. But though this sort of fact collecting, he's exactly talking about this collecting of facts, empirical facts, has been essential to the origin of many significant sciences, anyone who examines, for example, Pliny's encyclopedic writings or the Baconian natural histories of the 17th century will discover that it produces a morass. One somehow hesitates to call the literature that results scientific. The Baconian histories of heat, color, wind, mining, and so on are filled with information, some of it recondite. But they juxtapose facts that will later prove revealing, e.g. heating by mixture, with others, e.g. the warmth of dung heaps, that will for some time remain too complex to be integrated with theory at all. So in some sense, just collecting data is not helpful at all. And as Kuhn says, maybe one hesitates even to call it scientific, because in some sense the structure is missing, and the structure is in his sense given by the kind of paradigm you're in. Now, we don't have to be Kuhnian to see that this is a kind of relevant point, that you cannot kind of ignore the setup within which you want to find empirical facts in need of an explanation. So that's why you already see Popper not talking about kind of this problem as something empirical, but as kind of, he still talks about empirical facts, but he kind of poses that within a framework and a theoretical background. So if you want to explain tides, you include circular inertia and you take a Copernican viewpoint, for instance, but you can also take, of course, different setups. This is what determines the problem, right? The scientific problem you're posed with, you're not suddenly trying to solve the neutrino problems with Einstein's GR, right? There are certain domains, you have certain theories within which you pose the problem and try to solve them. And then you also identify, so Agassi, for instance, recognize the importance of metaphysics in defining scientific problems. This may seem odd. At this point, I will get back to that later on. So I kind of want to pose it to you now. If you think, for instance, that, about neutrino physics, some questions that came up during this week, I'm sure, were, for instance, why are the neutrino masses so small? Do right-handed neutrinos exist? Is the neutrino its own antiparticle? Now ask yourself, which of those are actually empirical facts, right? You could ask, well, we know empirically that the masses of neutrino is small, but why do you need to explain that, right? So if we know, for instance, the mass of the electron, we know the masses, and these are kind of empirically determined values within the standard model. Why is the neutrino mass so special? Well, it's small, it's tiny. But just because it's tiny, we have to explain it? Well, you see, the reason, you can give a reason, and you will give a reason, but that reason is within a certain theoretical framework, within which that becomes a kind of pressing question. Similarly, questions about, for instance, is the neutrino Majorano or Dirac? These are questions which don't even make sense without the theoretical framework within which they are posed. So let me come back to this question and kind of give you a more precise kind of account of the scientific problems, named Tom Nichols' constraint inclusion model. So Nichols' account of scientific problems goes as follows. So he defines problems, scientific problems, in the following way. He says a scientific problem is the demand that a certain goal be achieved plus a set of constraints. That's it. So he doesn't write it like that. I just write it like this because later on you will see why. So you have a goal and you have a certain set of constraints. I haven't told you what these constraints are, but you have a set of constraints which in some sense together are constituting your scientific problem. So when you ask the question, what is a scientific problem? Well, that is a scientific problem. Now, there are several things that follow from. So first, there is no clear distinction between, for instance, empirical and conceptual problems. You sometimes hear that there are these empirical problems and there are the conceptual problems. That's a position, for instance, that Larry Laudon, another philosopher of science, defended before Nichols. Now you don't have that because the constraints are part of those constraints are empirical, part of those are conceptual. They are not distinguished. It might be that your goal is more in identifying, kind of providing an explanation for an empirical fact, but that doesn't make it an empirical problem per se, because it's still the problem arises within the constraints, which are theoretical, metaphysical, etc. I will show you more about how that comes about in a second. So second, he says that there is no kind of algorithm which gives rise to scientific problems. You have to kind of find them. You have to find these different questions you want to pose and work within this constraint to solve them. And some you can just solve, and that's straightforwardly. And sometimes they are more problematic, more difficult. And now this is an important point, which is sometimes forgotten, because that even though you have the certain goal, not all constraints are usually known. That is, there might be possibly a tacit constraints in the background within which you work, and you have never identified as something that are actually constraining the way you can approach that question. So in some sense, you can see the possibility of developing a scientific problem because you kind of identify more and more constraints within which you're developing your set of solutions. So let me go through some of the consequences so you get an idea of how this account of Nichols works. So now you have the position that two scientists may disagree on the set of constraints, although sharing the same goal. How can that be? Well, they share the same goal. They want to explain the same thing. For instance, find a theory of quantum gravity, a consistent theory of quantum gravity. Now, they disagree about the set of constraints because, well, if I come, for instance, and this is actually a case that you can analyze, and people have discussed that, you have different theories of quantum gravity, right? You have string theory group, you have the loop quantum gravity. Loop quantum gravity grew out of general relativity. String theory grew out of particle physics, right? Once you develop these kind of theories, you see that the set of constraints in the GR context may be different than in the particle physics context. And so your assessment of what is possible is different, right? So in if you come from GR, you want to have a kind of what is called background independence. While in particle physics, you work perturbatively all the time. So you have a fixed background on which you look at the perturbations, right? And so that's not problematic if your theory of quantum gravity to some extent have that feature as well. So you see that these can be different. So the disagreement is in a set of constraints. So in some sense, his account has the kind of ability to make sense also of the kind of the discourse within science itself. And so he also says some constraints are more fundamental, more important than others. That's obviously the case. Sometimes I introduce a certain constraint, a certain way of doing things for pragmatic reasons. I use certain approximations that there is no fundamentality to that. It's just that's the easier way to do it. While others, like I require my theory be Lorentz invariant, seem to be more fundamental, more important. And through that, it follows that some problems are just deeper than others, and there is historical evidence for that. And in that account, you can actually make sense of that. I should put the ball away here. Don't need that anymore. And he says, now the following, he says, the problems can be reformulated in significantly conceptually different ways, formulated more or less completely, transformed and reduced to other problems, all without essential change in the presentation of the empirical data to be explained. And that's an important point. That is, if I fix the empirical data, I can see that the scientific problems still can change significantly, even though the empirical facts are in some sense fixed. And that shows you kind of both the strength of his approach as well as the kind of difficulty of the positivist picture. And this is important for me. He says that formulating a good problem can be an important theoretical scientific achievement. It's already an achievement to formulate a good problem. So let me, that's a list, not he doesn't mention a specific list, but that's just a list that you can come up with. I wrote down several things that could be elements of that set of constraints within which you work. So first, there's obviously empirical evidence. Then you have physical assumptions, like invariance, etc. Then you have certain metaphysical assumptions. I will mention one in a second. You have theoretical framework. Think of quantum field theory or quantum mechanics or classical mechanics or whatever. Then you have certain mathematical methods with it, which you use to solve those problems. And these are constraints because you might want to change them. You might not be aware of other mathematical methods. Maybe you need to develop new mathematical methods in order to solve that problem. But at that point where you start, these are constraints. Then there are certain mathematical structures. For instance, when I use probabilities, I use the Kolmogorov axioms, which determine my probabilities. In quantum mechanics, I can't do that anymore. I use other probabilities there. When I do particle physics, I'm using group theory as the mathematical structure of my symmetries, right? I use Lie algebra, Lie groups, etc. So maybe this is a constraint. It's a constraint in the sense that I'm not using anything else, right? I could have, maybe I can weaken that. And there are historical examples which show that these are actually constraining the ways I can approach a question. If the time allows, I can give an example for that. So, and now this is all abstract, so let's apply to a straightforward case study from particle physics. So the Higgs naturalness problem, one of those problems which has guided most of the standard model particle physics in the last couple of decades. So the standard, this is a kind of standard formulation you can find in textbooks, right? So the Higgs naturalness problem arises due to huge quantum corrections to the Higgs mass. Don't worry if you don't grasp the details if you haven't studied quantum field theory or ionization group theory. But the point is mainly, if you want to calculate, you can calculate the physical mass of the Higgs, and you have some kind of Baire parameter, and then you have corrections to that. Now, for all of the other particles in a standard model, which are not scalar, because the Higgs is the only scalar particle, you actually, the corrections are not affecting the physical mass, which goes logarithmically. Now, with the with the Higgs mass, you actually get quadratic divergences. So if lambda usually would go way up, it doesn't matter because the logarithm doesn't kind of go with that, right? But if it quadratically diverges, it depends on where the cutoff is, right? How big that is. And usually you take that to be a scale where you expect new physics, okay? So if I take the new physics where we know new physics to happen, which is the Planck scale where gravity has to be taken into account, and I plug in some sense, I put lambda in here, I put the observed Higgs mass in here, then we can see that you need some extreme fine-tuning between this kind of bare mass and this factor to recover the 125 GeV Higgs mass. This is 10, so this is 10 to the power of 18 to the power of 2, right? So this is huge. So in order to, you need a huge amount of fine-tuning between these two parameters to recover the small Higgs mass of 125 GeV, relatively small compared to kind of Planck scale. Now, this cancellation fine-tuning requires a very unlikely conspiracy between the terms. Now, and that is a problem. Where does it come from, right? Why should they kind of, why should there be such a kind of unlikely conspiracy between these terms? So let me just kind of rewrite it in terms of the constraints that are being used. Sorry, I was just looking at the question. So now let me rewrite it into Nichols' account. Okay, so here you can just write it. So we have that tuple, that's a problem, right? The G is just the provide an explanation of the Higgs mass. That's our goal. Now, what are the constraints? You can just write them down. First one is the physical Higgs mass is 125 GeV. Then there is a huge gap between the Planck and the electroweak scale. That's the reason why this lump is taken. So this is the TeV scale. So if I go up to the Planck scale, that's a problem, right? So there's a huge gap between those, and that's part of the problem. And there is nothing in between. Otherwise, I would just go up to that scale, right? I could just put the cutoff at that scale. So, and then the QFD formalism is equipped with a standard interpretation. Now, there is much to be said about this, which I cannot go into that. But the standard interpretation, to some extent, interprets these as kind of, as I mentioned, these are energy scales. This is sometimes considered to be a fundamental parameter, and I will say more about it later on. Now, it's within that kind of interpretation of this formalism, this problem arises. And of course, there should be no unlikely conspiracy. You want that to be a constraint. You don't want to have a conspiracy between the terms. This is not something you want within your theory. As such, it is about addition constraint. And there are of course, many other tacit constraints that are not relevant for what I want to talk to you about. So now, this is the scientific problem I have now identified. Now, how do these problems relate to their solutions? I have to be way quicker. Okay. So as I said, stating the problem is already kind of half a solution. It's a scientific achievement to state the problem. And a problem determines to a large extent the space of solutions. How does it do so? Well, if you think about each problem constraint is a constraint on the solution space. If I weaken that constraint in some sense, I open the space of solutions in some sense. I can kind of expand it. So the answer that I will be following here now is that solution space is given by the denial of individual constraints. I should say this is not Nichols' position, but the way I kind of want to address that now. And each denial now corresponds to different strategies in theory construction. So let me come back to that example and illustrate what I mean with that. So once we have identified what the problem is, abstractly as a goal together with a set of constraints. Now, how do I solve it? Well, this is altogether, it's an inconsistency. So denying each one of those provides you with a strategy to resolve that inconsistency which is posing that problem. So you can deny the first one. Remember, you cannot deny that because to some extent it's an empirical fact. Right, so B, there is a huge gap between the Planck and electroweak scale. Your one strategy as well, bring the Planck scale closer to the electroweak scale. And that's exactly a consequence of extra dimensional theories. If you introduce extra dimensions, you make gravity in something, bring gravity closer to the electroweak scale. And that's exactly what the ADD model and the random sample model do. You can look at C, which is there is nothing in between, and just introduce new physics at the TV scale, as SUSY models do, as little Higgs models do, as Technicolor does. You can now go, and remember, D is a kind of standard interpretation. You can change the standard interpretation. So the standard interpretation gives a certain meaning to those parameters in a physical sense about energies, relations about energies at different scales. Now, already Wetterich argued in '84, and two of my colleagues of the LHC research unit have defended the position that, well, you don't have to do that. There is nothing, if you look at it, if you look at this, this is what I actually physically measure. This is nothing, it doesn't have to have a certain interpretation. And they show under what conditions you don't need to kind of interpret them in an, give them an interpretation in a metaphysical sense of something associated to the real world. And within that account, you can show, you can show that, well, this just becomes a kind of convention. You can conventionally choose something. Just as I choose the coordinate system to be such and such and not different, because in that context it simplifies, the choice of what the bare parameters is similar, they argue. Now, another way is you kind of address the measure problem. When you talk about unlikely conspiracy, what does that even mean? So Hossenfelder has argued, well, there is no unlikely conspiracy unless you put a measure on it. You have to, when you talk unlikely, you talk about probabilities, and the theory itself doesn't possess this probability. So you have to put a measure on top of it, and you shouldn't, because it's not part of the theory. So you, once you give that up, you have solved that problem, right? You don't have that. There are other approaches which I don't have time to talk about. Now, if you look at it, these are the new theories which grew out of this problem, right? The proposed theories to solve that, extra dimensional theory, these, and string theory. This is way beyond, this is more complicated, but these at least are, were being tested at the LHC, and all of those were almost completely disconfirmed to a large degree. So the non-observation of beyond the standard model of physics at the LHC puts pressure on the naturalness principle. So Giudice, for instance, talks about the dawn of the post-naturalness era, and one should know that Giudice is one of the main defenders of the naturalness principle. So in some sense, you can recognize this, you have a scientific problem. It led to the development of all of these kind of approaches, all of these theories. All of them were disconfirmed. So you kind of think maybe the problem was not a problem in the first place. Maybe it's not something we need to address. And that amounts in some sense to those which do not provide you a new theory, but just say, well, our constraints were false constraints. So now you have in this kind of post-natural analysis, you have positions ranging from arguing against the cogency of the principle to assuming that one way or another, that's Giudice, naturalness will stay and play a role with us in the post-naturalness era. Practice, what's actually happening now, if you talk to physicists and particle physics, this has actually led to a rise in more theory-independent searches. So you do not develop theories which are going to be tested at the LHC or new colliders, but you try to identify signatures to be found in the new colliders. In some sense, you try to be as theory independent as possible because, well, theory didn't help much in the last round. Goes on the kind of EFT approaches or a simplified model. Okay, let me go through now through some of the strategies that I already mentioned. You already saw the relation now between the problem and the solutions from a kind of more abstract way. Now, let me go through some of the strategies that are being used. Ignore the first, this is just a way to kind of understand what is going on. But the first one is, well, you can change, these are the ways you can change a scientific problem to make it, to tackle it in some sense, right? And there are many different ways you can identify and actually you can show how the problems can actually vary during the time, the development of the field itself. So for instance, one simple way is you find new constraints that play a role in identifying the goal. So you have, for instance, you just find, for instance, new empirical data. That is, think about the Higgs naturalness problem before they actually measured the Higgs mass. Before that, there was a certain range, and there were many other theories which proposed different Higgs masses. So non-commutative geometry did some predictions, etc., etc. But those, once you fix the mass to 125, you rule out a set of other solutions, right? So additional empirical data extends the constraint set. But also, these don't have to be empirical of that kind. When Bell developed his Bell inequality, for those who know philosophy of quantum mechanics, when Bell introduced his inequalities, in some sense, he put constraints on future completions of quantum mechanics. People who tried to complete quantum mechanics with hidden variables needed to now take into account the Bell inequality, which rules out a huge set of possible solutions to that question. You can reduce the problem. So what is meant with that, in some sense, you take your goal and replace it with a denial of one of the assumptions in your constraint set. As I said, if your constraints, if you together they're in some sense inconsistent, then the denial of that amounts to a new goal, and you can just focus on a subproblem. That's exactly what you did when you try to solve the hierarchy problem, and through solving the hierarchy problem, you solve the small Higgs mass problem in some sense. Or if you introduce TV scale physics, you can address similarly the question of the small Higgs mass. Another way of reduction, which let me skip that. It's in some sense, it's just you can decrease the problematic tension in some sense. There are ways to do that, and there's an example I mentioned about extra dimensions, how to do that. You can reformulate problems sometimes, and this is something you can often find. So Nicholas nicely said it. He says logical equivalence does not entail cognitive equivalence. Just because two ways of representing the same thing is logically equivalent, it doesn't mean that we are able to grasp them in a similar way. And this is often the case. For those who have already heard some quantum field theory, you will always kind of go from 3+1 Minkowski space to 4D Euclidean space because it's just much easier. And then you go back to Minkowski space. So you reformulate your problem and then you go back. Then you have what I call problem precisification. People don't like that name. I don't either, but I don't know a better name. Anyhow, so there the idea is what you consider to be a constraint, you need to make more precise, and through that more tractable. So before the E was, for instance, there should be no unlikely conspiracy. At the beginning, when the naturalness problem arose, people were talking about this kind of, there is some kind of unlikely fine-tuning going on between these, but they didn't kind of made it more precise. And later on, Barbieri and Giudice, and later Castano and Anderson and Castano and others introduced the measure of fine-tuning, so probability measure, which can now be discussed and which can become within a more concrete program a way to address the question by saying, and we gave rise to that specific measure. Think of kind of top-down approaches, for instance. You can relax the problem. This is something I mentioned when I was briefly when I was talking about the mathematical structure. So what you do here, so you have a set of constraints, right? And think of the mathematical structure. Now, if so Lie algebras, let's take the example of Lie algebras, that's this one, satisfy certain axioms. Now I can relax those axioms. Sometimes, for instance, if I go from Lie algebras to so-called graded Lie algebras, I actually relax the constraints of the, so in some sense, any Lie algebra satisfies the axioms of graded Lie algebras, but not all graded Lie algebras satisfy the axioms of Lie algebras. So what happens is now I mathematically expanded the way I can address the question. And when people try to kind of develop or combine internal and external symmetries in particle physics, they showed it is impossible. And this was actually the strategy by which they were able to still be able to do that and develop, and well, was supersymmetry, which was able to then combine them. So this shows nicely is a way how these constraints can impose really restrictions on the way you can solve the problem. Okay, I'm out of time. Let me briefly sum up what I wanted to tell you about pursuit worthiness. So we had these problems, and when you talk about pursuit worthiness and justification, we now have a straightforward way to ask that question, namely, can we justify these? Because what makes the problem are these. So the question is, can I justify these? Now, some of them, well, yeah, empirical data, I have experimental ways to test them, I can do robustness analysis, blah, 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 right? But with others, it is less straightforward. What does it even mean to justify the methods of something, right? But these are what determines the problem. Or the metaphysical assumptions, another example, right? So the question is, what are the possible justifications I could have? How do I usually justify stuff? So for instance, I could have empirical justification, right? So I measured a certain Higgs mass. I didn't observe anything else. These are empirical justifications for certain constraints, and they're quite strong. But I could also have metaphysical justifications, for instance, along the lines of what parts of the formalism should be interpreted physically. Those who argue against my two colleagues, for instance, want to say, well, once I give up this kind of interpretation of the bare mass, etc., then I'm actually losing a certain amount of kind of metaphysical picture about emergence and reduction in particle physics, because these links between this kind of lambda is a way to link different scales, and the naturalness is nothing else than an assumption about the independence of these scales that you want to have, right? So if once I give up this interpretation, this might impact this intuition we want to have about the kind of energy scale of particles. There might be meta-inductive justification. What do I mean with that? You have a certain theory, you have a certain constraint, and you want to keep that constraint also in your future, and it's meta-inductively justified in the sense that in the past, whenever I required that to be a constraint, it actually led to empirically adequate theory. So I have, on the history of science, good reasons to keep it as a constraint also now. And there might be pragmatic justification. It's just simpler to take that constraint rather than taking something else because I just don't know what else to do. So the strength of the justification one can give for various constraints varies significantly, from strong empirical evidence to simple stipulation of preference. And in that context, it's just difficult to assess what it means to justify a problem. And one thing one should not forget, that what the pursuit worthiness may not only be about the justification of the individual element, but also about the fruitfulness. Many talk about the naturalness problem as being incredibly fruitful in developing theories beyond the standard model. There might be cultural social elements, just quite popular in a certain area. There might be about abilities and tools. So whether I should pursue something is, well, I do have the tools to do it, so I do it. And yeah, so there is much more to be said about this, which I won't do. I actually don't have much more slides anyhow. So let me end here and open the floor for questions. So let me know.
Thank you so much. That was absolutely brilliant and so interesting. I think we have a couple of questions, so I'll let you answer them now. And thank you again.
Thanks. So how do I see the Q&A session?
So it should be at the bottom of your slide, of the screen. There's just a little function that says Q&A. It might have like a little red notification saying
I had the wrong one.
Questions. Oh, right, okay. Yeah, there you go.
Okay. So how do we figure out what can be useful to measure outside of our assumed constraints? Well, good question. You don't, right? In most circumstances, you have certain. So I mean, you have to if you look at the LHC physics, right? You're looking for Zuzi extensions, and you want to test the extensions of the standard model, right? Like the MSSM and all of these extensions that have been proposed. And all of these have certain particles that you want to measure. And so with certain signatures. Now, LHC collects a huge amount of data. It's impossible to collect all of that data, right? So what they do, they drop all of the data, which is not all of that, but they put kind of trigger mechanisms in that kind of way beyond what is interesting according to those theories is dropped. They can't measure everything, so they measure what is relevant to test those theories which have been proposed. Now, in the kind of theory independent way to go about it, you will try to do that differently, right? Because then you would set your triggers completely differently. You don't have a theory to be tested, but you're interested to explore theory space in an effective way. And in that circumstance, you will use various ways to find signatures of particles, which might be something you hope for, but in a kind of more theory independent way. There is much more to be said about that, but it's physics details, and I'm a philosopher. So, but these are the strategies they use. I hope that answers your question. Let me go to the next question. For some measurements, we don't even know how to scientifically quantify, like potentially color or other things. How do we go about developing scientific use and arbitrary measurements? I'm not sure I understand that question. How do some measurements? Well, first of all, not everything scientific has to be quantified, right? Much of biology is not quantified and still science, right? So it doesn't need to be quantified. And but if you think in physics terms, usually you do have numerical values you associate. And if you think of well, color, you can actually associate frequency with the color and measure it. So I'm not sure I understand what's meant with arbitrary measurements. So if you want to kind of elaborate on that in the question, feel free to do so, and I kind of get back to that. Developing scientific measurement methods. That's not a developing scientific. Yeah, I'm not sure what that is referring to. Sorry. How to develop a theory-independent mindset when most of our experiments are based on testing theories? Well, this is a good question. So the question is how to develop a theory-independent mindset when most of our experiments are based on testing theories. So if you, the question is whether you should, right? In some sense, when Kuhn was talking about normal science, and he was to some extent arguing in favor of it. That is, being within a paradigm allows you to do certain things to such a kind of precision that you would otherwise never do. And this allows you to find exactly the weak points, which you otherwise would not do, right? So in some sense, being within one paradigm is not necessarily something bad. That's not the claim. The claim is that if you want to solve something, if you want to solve a problem, you can't do, recognizing that these are based on certain constraints within which you try to solve that problem. And in those circumstances, there is no kind of schema to follow to solve the problem, right? You cannot say, well, I do give up those. But of course, there are certain issues which you maybe just didn't come up. So when I was talking about the Lie algebra stuff, it was just they didn't think about it, right? So at that point, it didn't come even, it was such a tacit constraint. Symmetries are just represented by Lie algebra. That it was never a question whether this is still true if you change the mathematical structure. You actually can take different structures, right? You can go, I don't know, you can go to quantum groups, which are again a different mathematical structure, etc. So there are different mathematical ways to go about things, which you sometimes do not recognize. And so, but there is no schema to follow, but that will help answer. So there is not a straightforward way. That's just the kind of creativity of the scientists involved. What is the difference between meta-inductive and pragmatic justification? Are meta-inductive distinct? Yes, a good question. So the meta-inductive ones do possess, to some extent, good reasons. So the pragmatic ones, I am aware that this is the kind of assumption that I do in order to solve that problem, but nothing commits me to that, right? So in some sense, when I use certain approximation methods, if I make an assumption or use a technical method, just using it because that helps me to kind of to get me to the next step, nothing commits me to that. Now, in the meta-inductive, I actually have over the history of science support for that claim. So when I was thinking fine-tuning, so if I go, there is a colleague of mine, Miguel Angel Carretero Saiculo, he wrote an article where he looked at previous applications of the naturalness principle in the history of particle physics. So what happens, so if you go back, there are cases where which you can historically reconstruct that if you would apply that principle in that circumstance, it would have made a prediction about the mass of a certain particle, the charm quark, and it would have been able to, and then it turned out to be right. So in some sense, in the past, whenever I used that principle, it turned out to be leading to empirically adequate predictions. Therefore, now I should use it as well. It's an inductive step, but it's on the history of science. That's why meta-inductive. And I might be less willing to give that up than a kind of just purely pragmatic one. I hope this answers the question. Whoa, there are new questions coming up. Wait. They're gone, right? I thought there were other questions, but I think they are now done. Okay. There are now another question here. Are there other experimental methodologies that would be used to identify potential issues with existing theories? I'm not sure I understand that question. So experimental methods is just doing experiments which either agree or disagree directly or indirectly with predictions of the theory. Does that, I'm not sure I understand that question. Okay, oh yeah, now I see. There, sorry, I thought the question, now I see there are some, okay. Okay, so there is a general question about the work the epistemology of the LHC group does, what sort of work you guys do, how linked is the group work with the work from scientists at the LHC? It's directly linked. I mean, the people involved, the physicists involved are people, theoretical physicists and experimental physicists involved in the LHC experiment, both in research and development and current analysis. So these are physicists which are in joint projects addressing questions together with, so it's always 6 projects, and each project is always, there are always physicists in each project, as well as people reflecting on the physics with them. So the first project is about virtual particles, together from a historical perspective with 2 historians of physics in Berlin, historian philosophers of physics in Berlin. The A2, the Naturalness problem one, is where I work with together with a theoretical particle physicist in Aachen, where we look at the, well, to some extent, the physics itself and address questions about what that principle actually means, how it was applied in the history of physics, and whether they are similar, they're different, and how it was applied, how it changed over time, etc., etc. And so there is one project which is on the sociology of the LHC physics. How does, for instance, questions of novelty arise in that context in the big scientific community? There is one project which asks through experimental methods questions to the scientists. So they send out huge, they gather a huge amount of data from the scientists involved at the LHC to get info about what they think about the theories and how they assess those theories. And so check out the LHC epistemology website. All of those projects are there with also the publications of that project. Now, next question. If we do not consider non-interesting data collected in LHC, I think that in theory-dependent experiments can be subjective. Are there ways to resolve this problem? How do experimenters keep their interpretations objective as possible? Well, the problem is you're assuming that the interpretation of empirical results can be subjective. In what sense Can you add something on that? Because it's not sure in what sense it could be, what you mean with subjective. There's just, you try to kind of get rid of the kind of theory dependence in your search. So you explore the space. So in some sense, you take the standard model and you explore the possibilities to extend it in a non-theory dependent way. Of course, this is just possible to some extent because it's, you are within QFT. So it is at least QFT dependent, but you're not specifically extending to include Zuzi particles, for instance, or whatever. So you kind of explore through higher order terms in your Lagrangian possibilities to explore that space in a certain way. You try to build in some structure, but again, I'm not an expert on that to be helpful anyway. But I'm not sure what you mean with subjective, sorry. I meant by subjects that we might get to only look for evidence that can support the theory. Well, if you don't have a theory, you don't do that, right? The subjective element might be that if I constrain myself to that, I may miss signals outside of those data that I'm actually looking for, right? But in this case, I might find only those theories that I actually know that I propose. And in that sense, it's more subjective in the case where you actually do have theory compared to the situations where you don't have theory, because there you're more objective. I would be hesitant to call it subjective though. It is an attitude which has been associated also with Kuhn, but it doesn't have to be. So, but this is a larger discussion. I hope this helps. So, Prashasti Tiwari asks, science of physics we are taught and we know of is quantified. When you say not everything scientific has to be quantified, could you elaborate on this? Oh, I didn't mean physics. Physics, obviously, everything is quantified, but what I meant is really, you wouldn't say just because many issues in evolutionary theory are not necessarily quantified, it is not science. I would say biology is science. So one has to be careful about judging what is scientific and what is unscientific. So there is a long debate within the philosophy of science literature about criterion or demarcating science from non-science, metaphysics, pseudoscience, or whatever. And there are problems with most of those accounts, and none of them, I think, would require quantifiability as a requirement for scientific, for being scientific. So yeah, you don't have to be scientific. You don't have to be mathematized to be considered scientific. Going back to our, I hope this answers your question. So Munib Safar, going back to our earlier discussion on Zuzi, does the exact same framework of thinking apply to exotic theories such as string theory and loop quantum gravity, or do we modify our approach when scrutinizing them? When you say does the exact same framework, you mean that of assessing theories based on the way they solve problems? This is one framework. I mean, there are various ways of assessing theories beyond the standard model, right? And in the context of string theory and loop quantum gravity, to some extent, you can say they satisfy problems. They kind of solve certain problems. They provide consistent theory. They recover theoretical evidence in sense of, for instance, you independently developed a formula for black hole entropy. And then you look at, from a kind of quantum field theory perspective, and then you, from string theory, you try to look at black holes, and you get the same entropy formula. So these are kind of what Richard David calls unexpected explanatory coherence. And these are, again, no empirical theory, but they are on the meta-empirical level, they constrain the set of possibilities that are able to do so. And as such, they provide evidence in a non-empirical way for those theories. So these are being used, they are being used everywhere, right? So even in those cases where you have empirical results, you can use them, but in those circumstances, you just less willing to do so, because empirical results are just more reliable than these meta-empirical ways to assess your theory. I hope that answers your question. Okay. What sort of work have you or your group done regarding renormalization theory, if I may ask? So the question that comes up, this is a more technical question, and also these are the two people I mentioned, Joshua Rosala and Robert Harlander in the A2 group. They are concerned with the role of RG in the context of naturalness assumptions. And to some extent, what you can show, and this is following Betteridge, is that when you renormalize, there is a certain kind of scheme dependence with respect to those values, which you should not have. And their argument about the kind of conventionalist approach is along the line, is linked to this kind of analysis of RG techniques and scheme independence. Sorry, I'm thinking about if I elaborate, but that would take way too long to become more technical. But if you're interested, if you go to the LHC epistemology group and go to the subgroup A2, which I'm part of, they have 2 papers on that subject matter where they explore these issues. Great. Any further questions? What projects, experiments have been theory independent? Well, those that are current. So the question is, what projects have been theory independent? Those that are being developed now, as I said, since you don't have much guidance from theory anymore for future colliders, the idea is to exactly develop theory independent extensions of the standard model in some sense and test those. Yeah, that's what they're currently doing, and with those simplified models. Simplified models are still a little bit theory dependent. All of them are to some extent theory dependent. You need to do some theory dependence. It's just very difficult to be completely theory independent. But yeah, but again, this is something physicists is much more qualified to answer than I am. Do you think that quantum mechanics provides a problem for the scientific method because it seems like you can never be a subjective observer in an experiment? And when you make a measurement, you're directly affecting the experiment. Do you think that this could mean that we can never have an explanation for the quantum world? This is the kind of general philosophy of quantum mechanics question that would go way beyond anything that I talked about. There are different interpretations. Depending on what interpretation you take, there will be a different answer you will get for that. And there are good reasons for some compared to others. And it would go way beyond. And I think my position is not interesting enough to kind of elaborate on that. There are people who work on the philosophy of quantum mechanics who are better suited to answer that question about which kind of interpretation of quantum mechanics to take. So let me put it differently. There are observer-independent interpretations of quantum theory in which you get rid of that. And in those, well, you don't get that subjective attitude towards reality. I see no open questions.
Brill, I think that's all the questions done then, unless anyone has any last burning questions they'd like to pop on quickly. But I'm sure, I think you provided your email in the beginning, so I'm sure if people have some really interesting ones, they can always email you. Thank you again so much. That was absolutely brilliant. Thank you for sticking around and answering all of those. And I will, yeah, it was absolutely brilliant. I will pass on now to the president of the Maxwell Society, who will give just a conclusion talk on this conference. So thank you so much for being a part of this, and thank you for everyone who attended.
Okay, I'm just going to share my screen to show PowerPoint. Okay, yeah, so thanks everyone for attending this conference. The committee have been working really hard to make this happen, and we really appreciate your attendance for this because of that. And we hope that you really enjoyed this. So this is actually the first year we've run this online, obviously because of the pandemic, and we think it's been a great success as the first one online. So obviously we have the certificates that we had that you could apply for. So I'm just going to go over the certificates and what you can do to get them all. So with the bronze ones, all you had to do was attend all the seminar events and then mark the attendance through your survey using the validation word that we sent. So someone will be sending that again right now on the chat. And then we also have the silver ones, which is you have to fill in all the mini quizzes we send, and then you'll get a silver certificate. So again, those will be sent to you by email, and you just have to finish all of those quizzes by this Sunday at 11:59 p.m. GMT. And the questions aren't too difficult. If you watch the lectures, then you'll be able to finish those. So you should be able to do those if you just watch the lectures. And then finally, we have a gold certificate, and that's one where you just have to write a short reflection of 250 words or some sort of artistic thing you can submit, and you have to email that to us. So our email will be posted on the chat right now as well if you just want to email us from that. And the deadline for that is next week, Sunday, the 7th of March at 11:59 p.m. So with that, you don't have to do anything super complex. It doesn't have to be super deep thought reflection, just whatever you thought, whatever you learned, that's valid and that's important. So we want to hear about what you learned from this conference, whatever that is, and whatever you want to share. And then, so we'll also send email details about this from email as well, and you can fill that in and you can get your gold certificates. So do pay attention to the deadlines as well, and we'll try to get those certificates to you soon after the gold certificate deadline. And then, so tomorrow there's actually a different conference by our sister society at King's College London as well, the Women Physics Society. So I know you guys might be a bit tired after an entire week of conference, but I think it's still a fantastic conference as well. And even I'll be going as well. So it's the Women Physics Society, and they're running one about just the underrepresentation of women in physics. So they'll have loads of inspirational speakers and panel discussions. So we'll also send that over email, so you can sign up. And then finally, we have a survey, which we'd love for you to fill in. If you could please fill that in. Again, that will be on the chat right now, and by email we'll send it as well. So if you could fill that in, we just use that to improve our events in the future. And it'd just be great to know how you found this and if it was useful and good for you guys. Okay, so thanks, that's everything. Thank you so much for attending, everyone. And Radin, I just realized, thank you so much for your talk as well. I think we couldn't have made this without the amazing speakers, with our committee, and obviously with the attendees. So thanks so much. I think we're gonna stick around for another 10 minutes. If anyone has any questions about the certificates or anything like that, you can ask them, but otherwise feel free to leave, and thank you so much.